This event will be live on FB, so hopefully everybody on behalf and keep smile all the way. All right? Bismillahirrahmanirrahim. Can you start? Yeah. Bismillahirrahmanirrahim. Assalamualaikum and good evening to invited speaker in all. We are honored this evening to have with us Associate Professor Dr. Zurina Shaameri, who is going to share her knowledge with us. Currently, Dr. Zurina is a director at Institute of Science, UiTM. She also a senior lecturer at Fakulti of Applied Sciences, UiTM. Her research interest is on the synthesis of nitrogen heterocyclic with pyridine ring system towards bioactive natural compound, which includes focusing on the synthetic methodology and structural exploration of the ring moiety. Without further delay, I would like to call upon Associate Professor Dr. Zurina Shaameri to give her talk entitled Small Molecule, Big Potential, the Art of Organic Synthesis. Please welcome.
Tingginya Sufri. Okay. Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. So thank you very much, Mr. Chairperson. So our Mr. Chairperson was very serious. Selalunya Mr. Sufri is not as serious as this. I do not know why. Okay, so at first, I thought of moving around to interact with the audience and maybe to ask you questions. But I was told to stay put here because the camera is there. So I cannot move around, unfortunately. And fortunate for all of you. Okay, so my title, if you can see the title now, I have made some changes to the title, some addition to the title. So the title now is Small Molecules, Big Potential, the Art of Organic Synthesis. Okay, but please do not be afraid and do not be alarmed by looking at the title. I hope from this title, no one will walk out of this room. Okay, tak ada. I will not explain or teach you how to do organic chemistry or how to do organic synthesis, but I will share with you. Okay, so how we do our work, because I feel that my job here is not complete if I did not say something about organic synthesis. So I have to tell and explain a bit about organic synthesis. Now, everybody should have known by now, we, the organic synthetic chemists, when we do our research activities, at the end of the day, we want to synthesize a molecule, or rather a series of molecules, or analogues or derivatives. And these molecules mostly have potentials, have values, have benefits. So we do not only focus on the end product or the target product or the final destination, but we also focus on the journey along the way, because we have to really understand how we do the reactions, okay, the synthetic routes, in order to get to the final destination. So in other words, we have to have the required knowledge, the textbook knowledge in organic chemistry, but at the same time, we have to have some creativity and also some sense of innovation to do our research activity. So this is what I want to share with all of you. How to be creative and innovative when we do organic synthesis. At the same time, we're going to look at some small molecules with potentials, with benefits, and also with values. So, okay. Okay, so before I go into the main organic chemistry and the organic synthesis, I think most of you know by now that we have 5 main branches of chemistry. Okay, Siapa yang tak tahu we have 5 main branches in chemistry? Okay. So the 5 main branches of chemistry are mainly organic chemistry, inorganic chemistry, physical chemistry, biochemistry, and analytical chemistry. Of course, there are other branches of chemistry like environmental chemistry, like medicinal chemistry, pharmaceutical chemistry, environmental chemistry. But the main ones are the organic chemistry. These are the main branches of chemistry. Now, if I asked you, what do you think is the most difficult branch of chemistry? What would you say? Don't say organic just because I am an organic chemist. Which one do you think is the most difficult branches of chemistry? Some of you say analytical chemistry because Dr. Najma is teaching organic chemistry, so dia katalah in analytical chemistry. If you ask me personally, to me the most difficult branch of chemistry is physical chemistry. When I was in the university, physical chemistry is the most difficult subject to me, especially quantum chemistry. Siapa agree dengan I? Okay, and luckily I'm not teaching physical chemistry. So that's why I'm teaching organic chemistry. But if I ask my students in the faculties, okay, for the last how many years? I've been in UiTM since 1989. I just told them just now. I came in UiTM in 1989, so I've been teaching for 30 years already. So to me, when I ask the student what is the most difficult area of chemistry, many of the students say that is organic chemistry, because I'm teaching organic chemistry. But I think there are some truth behind it, because there are a lot of cartoon characters and caricatures indicating that organic chemistry is difficult. So one is, if you look at the one in the red box, I like that one. Before organic examination, everybody was sitting up straight. But after the organic examination, everybody is dying. Okay, so not only there are lots of cartoon characters, but also there are lots of organic books indicating or implying that organic chemistry is difficult. So there must be some truth that organic chemistry is difficult. Now, organic chemistry is actually a study to understand the chemistry of life. It's actually to understand the processes in life. We, the organic chemists, can work together with physicists, mathematicians, to understand how molecules behave. And we also can work together with biologists to understand molecules determine the life processes. We can also work with engineers. We can also work with chefs, for an example, chef yang dekat hotel catering tu. And we can also work with pharmacies. We can do a lot of multidisciplinary research with almost all disciplines of research activities. And do you know that now, at the moment, currently, there are 16 million known organic compounds? That's a lot. Okay, 16 million known organic compounds. And these compounds have diversified properties. They can be in the form of crystals, they can be in the form of oils, waxes, plastics, volatile liquids, and so on. But what I want to focus now is mainly on molecules or organic molecules which are small. Okay? Small molecules, normally we refer to those molecules which have about 300 grams per mole molecular weight or something like that. Okay, if it's bigger than that, they are not considered to be small molecules. So these are just some examples of small organic molecules, but they have values. Okay, they have potentials and they have values. So this is the structure of vitamin A aldehyde. So this aldehyde actually present in your eyes. All your eyes have this. Okay, it's on the retina of the eyes. And then this is actually the structure of serotonin. That is this is a human neurotransmitter. So serotonin, have you heard that serotonin and endorphin are your feel-good factors? The compounds that contribute to you feeling happy. So serotonin is one of them, and it's a very small molecule. It's just a 2 ring system fused together. Endorphin, I do not put here the structure of endorphin because endorphin is slightly bigger. The molecular weight is more than 300 grams per mole. So endorphin, it's a peptide hormone, but it is still considered quite small compared to the other bigger molecules. So this is the structure of cis-jasmone, which contribute to the smell of jasmine flower. And this is the mercinone, which contribute to the smell of roses. The smell of roses that you have is actually, the structure looks like this. And this is quinine. Quinine is an anti-malarial drug from cinchona tree. And that is the structure of not quinine, but structure of cinchona tree. Pokok dia actually is very big tree in the forest, and you have your quinine, which is an anti-malaria drug, which is quite considered to be a small molecules also. So these are examples of small organic molecules which have the good properties. Okay, and here are some examples of small molecules which have the bad properties. Okay, bad in the sense of dia bau dia tak sedap. Okay, so if you look at the structure of these molecules, what do you think they have in common? Apa yang they all have in common? They have what atoms? They have sulfur, right? Okay, this is thioacetone. Thioacetone ni, the British chemist in a soap factory in Leeds in 1890, they wanted to produce soap with efficiency to clean dirt or something like that. But they have problem mixing the solution. Somehow they have an excess of thioacetone in their mixture. So the smell of the whole factory was very bad. They call it a fearful smell. It is all due to thioacetone. Thioacetone is just simple structure like acetone, but you have an oxygen instead, you have a sulfur instead of the oxygen atom. Skunk spray. Pernah tengok skunk tak? Have you seen skunk before? Malaysian dia tak ada nama for skunk. Tapi Indonesian ada. The Indonesian call it sigong. Okay? Skunk is an animal that they spray or emit a certain kind of liquid whenever they meet their enemies or predators. Okay, so this skunk spray is very bad smell, and it consists of an aliphatic alkene with a sulfur substituents at the end. And ni durian, now we have durian season kan? Do you think durian have good smell or bad smell? That's because durian have a mixture of sulfur molecules and an ester. Sebab tu bau dia tak busuk sangat. Okay, so durian you have your ethane thiol and also this kind of ester, methyl butanoate. Okay, this was in the news last year in April 2018. Okay, a whole group, the whole library, Melbourne Library, evacuate the library because they thought there was a deadly gas leak, and they discovered that at the rubbish dump behind the library ada orang makan durian. Okay, this was last year, April 2018. Okay, so these are just some example of small molecules with their different values and characteristics. Now, organic chemistry, they're very much related to those activities of the industries and companies. Okay, the industries that benefits the most from organic chemistry is actually drugs and pharmaceutical industries. I think everybody knows that. Okay, because organic chemistry, chemistry-based companies make organic molecules from few kilograms to thousands of tons per year. So we have, for an example, companies that produce fibers for clothing. They produce 24 million tons per annum of a particular organic molecules. PVC are being produced 24 million tons per year. Okay, the most companies that benefits a lot from organic chemistry is DuPont, Monsanto, ICI, and ICI gain a lot of money also from organic chemistry base of research. That is, they can gain 10 billion Malaysian ringgit per annum. Okay, so do you know that there are institutions which focus on synthesizing or creating or generating flavors and fragrances just for perfume, cosmetic and food industries. Okay, dia punya function is just produce chemicals for all these perfume, cosmetic and food industries. So these companies, mainly there are lots in the United States and also in Switzerland. So if you look at the structure of these small molecules, they are all synthetic, but they have distinct smell and taste, okay, for these industries. So this is alkyl pyrazine. So that gives the coffee aroma, the one that you are drinking now at the moment. Maybe if you can get those and try to isolate and extract, you could get that as a molecule. I do not know. Maybe. Okay, so this is the structure of vanillin. This is the structure of menthol. This gives the sweet strawberry smell. That is for strawberry. And then this gives the smell or the aroma of a roasted caramel. And this is the structure of aspartame. Pernah dengar kan? NutraSweet. Okay, so even though NutraSweet ataupun aspartame have many political and medical controversies, but they gain a lot of money from their research and also company. Okay, like I've said before, pharmaceutical industries and also drug industries taking the most from organic-based research, organic chemistry. So these are just some examples of small molecules ataupun compounds in your drug components, your medicine. You look at this. This is ranitidine. Ini I selalu makan lah ni. Nama orang yang sakit gastritis and ulcer treatment. So the commercial name is Zantac. Okay, that is Zantac. And then this is atenolol. This is for treating and preventing hypertension, ubat sakit darah tinggi. Okay, and yang kat bawah ni, do I need to explain further? I think you can Google. That is Viagra. Okay, Google lah lepas ni. What is the use of Viagra? Now, like I've said before, my job is not complete if I didn't say anything about organic synthesis. Okay, so what is synthesis? If you look in the dictionary, by definition, synthesis is actually the process of making a desired compound using chemical reactions, and normally synthesis steps or synthetic steps involve more than one. Okay, so normally a series of steps involved. So that is synthesis. Why do we have to do synthesis? Maybe because we want to create ataupun to synthesize useful natural products atau useful natural compounds. Maybe we want to use it for industrially important compounds, and maybe you want to synthesize due to theoretical interest to prove a particular structure, and to developing a new synthetic methodology, and to develop areas in science and technology. So for these two, these are mainly for generating new knowledge. Okay. Now, before I go into details of the synthesis and also the asymmetric synthesis, do you know what's the difference between how do you say this? The organic synthetic chemist and the natural product chemist, because I can see that we have some natural product chemist here. Mana Dr. Nurizan? Dah hilang dah. Natural product chemist. Oh tu, sembang kat belakang. Okay. I was asking, do you know the difference between organic synthetic chemist and the natural product chemist? Okay. If you go to the pharmacy outside, okay, either you go to the Guardian or Caring Pharmacy, or even any established pharmacy, you look at the shelves on the pharmacy, in the pharmacy. Do you think that all the drugs, the medicine, the supplements, okay, are those natural compounds or synthetic? What do you think? Is it natural or synthetic compounds? They are synthetic. Why do we need to use a synthetic compounds for those drug components and not the natural ones? Why? kena tanya orang natural product. Okay, do you know that? Okay, I give you one example. This is a classic example which I always give to my students. If for an example, you have pokok tongkat ali. Okay, you have pokok tongkat ali. And then you look at pokok tongkat ali punya akar. Now, you have akar pokok tongkat ali. The natural product chemist will take all the akar pokok tongkat ali and they do their natural, their usual processes. They do their isolation, characterization, purification, not in those orders. And finally, they came up with one single molecule. Let's say kita name that molecule to be compound A. They came up with molecule A, and molecule A, they discovered that it has an anti-inflammatory properties. Okay, but in order to get 10 milligrams of the molecule A, you have to have tons of akar pokok tongkat ali. Betul tak? And then they discovered that this molecule A can be a potential component in a medicine for inflammatory property, for anti-inflammatory property agent. So all those medicine needs those particular molecule in a large amount. So in order to get that large amount of compound A, we cannot get from the natural resources. Kan tidak habislah kita punya natural resources, betul tak? So the natural resources do not have cannot meet the demand of the society and also the global community. So we have to synthesize them. So actually, you have a molecule that has a potential. The natural product chemists come from this end of the research agenda. They do their processes, their research, they came up with molecule A. But in order to meet the demand of the society and the pharmaceutical industry and the medicinal company, so the organic synthetic chemists have to come from the other end of the research agenda. So they have to synthesize molecule A from chemicals. So can you see or not? There are two different fields actually. But we always work together. We are like sisters. Betul tak Nurizan? Oh, betul. Okay, now, so how we, the organic synthetic chemists, synthesize molecule A? Before we do the synthesis, we have to look at the molecule and we have to do retrosynthetic analysis. Or another name for it is retrosynthesis. So I will show you how we do a retrosynthesis later. Don't walk out from this room. It's getting more and more interesting. Okay, so I will show you how we do retrosynthesis. But before that, okay, let me just briefly explain what asymmetric synthesis is. Now, does anybody knows what enantiomers are? Okay, yang non-chemistry ni ada ke sini non-chemist? So, if you have a chemistry background, if you took chemistry 101 in the university, you should be able to know what enantiomers are. Enantiomers are two molecules. I just use two molecules. Two molecules, they have the same molecular formula, the same structural formula, but just because one of its substituents have different orientation in space, okay, they are considered to be enantiomers. Okay, I give you one example. Let's say you have a ring system. Okay, let's say a ring system. Katalah I punya tangan ni a ring system. And the ring system have a hydroxyl group. Let's say the hydroxyl group is pointing upwards. You have another molecule where it has the same molecular formula, structural formula, but the hydroxyl group is on the pointing downwards. So the two molecules, they are enantiomers. These two enantiomers, kita can refer it as our hands. We have our left hand, we have our right hand. They are mirror images to one another. They have different properties. They have different properties in terms of their chemical properties are the same, physical properties are the same, but their biological activities or properties are not the same. They cannot be superimposed to one another. Okay, so we, the organic synthetic chemists, when we want to synthesize enantiomers, we have to know how to synthesize the enantiomers. That is what I said earlier, the first 5 minutes. We have to have the toxic knowledge and the required knowledge to do the organic synthesis. How we go about synthesizing the correct enantiomers is very important, because one enantiomer can be a remedy, the other enantiomer can be a poison. Okay, that is very important. So how to do that? That is actually asymmetric synthesis. So I give you one example. I've presented this before in FYP colloquium, but maybe some of you have seen this before. These two structures, if you look at these two molecules, they are the same. Nampak tak they are the same? They have the same number of carbon, same number of hydrogen, same number of nitrogen, and how they are bonded to one another are also the same. But the only difference is the orientation at this particular carbon. Okay, that carbon, these two molecules, they are mirror images to one another. The molecule on the left is considered to be the R enantiomer, the on the right is the S enantiomer. In 1950s, okay, in Germany, the R enantiomer was discovered to be an effective sedative. That means it is used to treat expecting ladies for combating morning sickness. Ubat alahan kepada morning sickness. Okay, so they distributed to all in Germany in 1957 because it is used as a medicine, as a sedative. But later, in the late 1950s, it was discovered that many children were born with flipper-like limbs. Flipper-like limbs tu maknanya their hands are like seal, anjing laut. Okay, so somehow the S enantiomer is actually a human teratogen. So that means it can alter the DNA of the human. Okay, so the researchers at that time were wondering why is that they gave to these pregnant expecting ladies the R enantiomer, but suddenly they have all these flipper-like limb children being born. So they discovered that when they give the R enantiomers, our body, which is very acidic, especially in the stomach, the pH in our body can cause the molecules to undergo racemization. So the R enantiomer undergo racemization to produce the S enantiomer. So that causes the children to have to be born with flipper-like limbs, and these babies are called thalidomide babies. So the thalidomide was stopped in the late 1950s. Okay, after they discovered the cause of it. So another example of the importance of enantiomers or chiral molecules is actually limonene. So if you look at the R limonene and the S limonene, the R limonene has a very sweet, fresh citrus smell and flavors, but the S limonene has a very harsh turpentine-like pungent odor. So they are different. The structures are the same. It's just that the orientation of the substituents are different. So that's why they have these properties differently. Okay, now I want to share with you how we do synthesis. For the past 15 years, okay, our group has been around for the last 15 years. For the past 15 years, we have done a lot of retrosynthetic analysis or retrosynthesis, like I've said just now. But I just want to share with you one retrosynthesis which I consider to be a very simple one, okay? Because it consists of only 4 steps. It's very short. We have many retrosynthesis before which have longer steps. Okay, betul tak Fazli? Fazli diam aja. Dia punya yang panjangnya. Okay, when we do, like I've said just now, this is an example, a streptopyrrolidine. This is an angiogenesis inhibitor. It is used to stop atau to prevent the formation of new blood vessels. So it has been known to be used as an anti-tumor agent, okay, to stop the growth of a tumor. So streptopyrrolidine, if you look at the structure, kalau I give the structure to Dr. Najmah, Dr. Najmah will do retrosynthetic analysis maybe in a different route. I give to Dr. Tajuddin. Tajuddin maybe will do it in different route. and I look at the molecule, I will do it in this way. Okay? Whenever a person do retrosynthetic analysis, you do not have to do it in the lab. You can do it anywhere. You can do it in the bus stop. You can even do it here. Okay? Because this retrosynthetic analysis is just theory on paper. You do not have to be in the lab. When you have to be in the lab, bila you dah purchase all the chemicals required for the synthesis, baru you masuk lab. When you are in the lab, then you do the synthesis following the route that you have prepared. Okay, so that's what we do. We want to synthesize streptopyrrolidine. What I meant by retrosynthetic analysis is we have to break the molecules parts by parts, functional group by functional group, until we come up with readily available starting materials and cheap. Dia mesti cheap. So, that's what we did. For an example, you look at the structure of streptopyrrolidine. If you have chemistry 101 in your university years, you should be fine. You do not have to have chemistry subject, organic chemistry. Okay, the difference, I can say that this molecule can be prepared from this molecule. The difference is that, can you see the hydroxyl group? And can you see the ketone or the carbonyl groups here? So meaning that streptopyrrolidine can be synthesized from this molecule by letting this molecule undergo reduction to produce this. Then kita work lagi ke belakang. It's reverse engineering tau, work backwards. If you want to synthesize this, how to synthesize this? To me, we can synthesize this from this molecule. That means kalau kita remove ni, we can get this. And then how to synthesize this? From this intermediate diester. That means if you let this compound undergo Diekmann cyclization, you can get this. And how to synthesize this is actually come from an amino acid, which is phenylalanine, and just a malonate ester. Okay? So, by doing the reverse engineering on paper, secara theory, what we do is, we buy these chemicals from, bukanlah from Giant or Aeon, kita buy from Sigma Aldrich or Merck or something like that. So kita masuk lab, so we do the condensation reaction. Do condensation reaction, Diekmann cyclization, decarboxylation, reduction, and yes, we get your streptopyrrolidine. Nampak tak how easy it is? Easy kan? Ask those students at that corner, senang ke tidak? Okay, so that's what we do. We let it undergo condensation, and then we perform Diekmann cyclization, and then we have to remove this by decarboxylation reaction. I tak nak explain the chemistry, okay? Because this is supposed to be santai-santai. And then the last step, you have to really know your chemistry, okay? If you look properly at the molecules, these two carbons, okay, dia ada two chiral centers. Maksudnya, the hydroxyl group and the benzyl group can either be, let's say for an example, this is a ring system. Let's say my hand. Your hydroxyl group can either be up, benzyl group can be up, or the hydroxyl group can be down, the benzyl group can be down. Or, one is up, one is down, one is up, one is down. Betul tak? So, there are 4 isomers. Like I've said earlier, one can be a remedy, the others can be poison. So when we do organic synthesis, you have to use your knowledge in organic chemistry, how to synthesize the required structural conformation. Itu yang pentingnya. Okay? You cannot simply just synthesize for the sake of synthesizing dapat molecule. You have to check the structural configuration just to make sure that you produce the right molecule. Kalau tidak, susah. Okay, and then, so to make long story short, the last step actually we have to really look into the correct reducing agent. Okay, we use triacetoxyborohydride, okay, to obtain only the cis isomers. That means both hydroxyl and benzyl group above the ring and both hydroxyl benzyl group below the ring. Yang trans, kita manage to remove it as a minor product. And once we manage to get the cis compound, you still have to know how to separate the two, the RRSS from one another. So that's what we do. Okay, so in other words, when you do your organic synthetic research, you really have to know how to go about doing it. That means your fundamental, it must be really, really strong to know your correct stereoselectivity, regioselectivity, and chemoselectivity. Okay, another example, okay, that work just now was performed by my master student, Sharifah Hidayah. Now dia dah jadi entrepreneur berjaya. Okay, so this is another work which I want to share, a very short one, a quick one. Pachydermine. Pachydermine is performed by another of my PhD student, Dr. Nur Hidayah. She's not here. Dia kena balik Kuala Pilah this afternoon. Okay, so Dr. Nur Hidayah, since I have too many hidayahs in my life. Okay, I dapat banyak hidayah. Sharifah Hidayah and Nur Hidayah. Taufik mana? Oh, Taufik Hidayah. Yes, Taufik. Sit down. Okay. Okay. So, remember I said earlier that you have to have some sense of creativity and sense of innovation when you do your organic synthesis. This is what I meant. If you look at the structure of pachydermine, the pachydermine can be divided into 3 sections. Oxalate subunit, the ring system, and the benzylidene. Now, if you do organic retrosynthetic analysis, you can split the molecules into 3. That means the oxalate subunit is branch A, the benzylidene group is the branch B. So I will not go into detail of this. If you want to synthesize the branch A, the starting material will be ethyl oxalate. Okay? If you want to synthesize the branch B, the starting materials will be just a benzaldehyde with the correct substituents. So, what we have to do is, kita beli ethyl oxalate and benzaldehyde, and also you synthesize this intermediate ring. So, how to do this intermediate ring, synthesize the intermediate ring? Like I've explained before, you have to purchase ethyl malonyl chloride and a glycine, just an amino acid. So, what you have to do in the lab, synthesize these two together until you get the ring. Then you just insert something at the C5, the benzylidene, and then at the C3, your oxalate subunit. Then you dapat pachydermine. Senang tak? Oh, senang. Betul tak? Hidayah tak ada. Kalau tidak, I boleh tanya dia. Senang ke tidak? Kalau tidak, dia takkan tak habis PhD 4 tahun. Mesti susah. Okay? So, now, if you do retrosynthetic analysis on this molecule, the starting materials would be this. Itu I punya observation. Maybe if I ask Fazli, Fazli will think it a different way. It all depends on the individual, how they do the retrosynthetic analysis. Now, if you use this as a starting material, the target molecule, when you do retrosynthetic analysis on this, the starting materials are different. Now you have diethyl oxalate acetate and a glycine as the starting material. So when you do the synthesis in the lab, this is what I meant by you have to be creative and innovative. Bila you couple the two starting materials, you dapat these intermediates, and when you want to perform cyclization, you notice that the nucleophile, which is the amine attacking the ester group, now ada 2. It can attack this ester to produce your expected compounds. This is the one that you want. Tapi if this nucleophile attack the other ester, you will get this. Okay, so I always tell my students, whenever you have or you get compounds which are not what you expect, jangan anggap dia sebagai failure. Anggap dia sebagai an opportunity to open up to a new chemistry. So you have to be creative and innovative. And that's what I always tell my students. Maybe the younger ones I lupa nak beritahu kot. The older ones, so I always nasihat them. So you have to look into the different aspects of organic synthesis. Then you can start to explore this molecule. So these molecules is considered to be a new chemistry. And by the way, Nur Hidayah did not proceed with this. So adalah candidate siapa yang nak boleh continue with this. Okay, so this is what actually she did. She managed to get the advanced intermediate for pachydermines in maybe, I think with overall percentage yield of 5 or 6. Okay, that's all about organic synthesis. Just want to share with you a bit about iOS. Now, Institute of Science, we have 6 centers. Okay, ni sekejap je, 10 minit. 10 minit. Maybe 5 minit. Kita syuk habis pukul berapa, Tuan Pengerusi? See? I still have 10 more minutes. Okay, so if you look Institute of Science, we have 6 centers. Okay, our center is actually Center of Synthesis and Chemical Biology. So the researchers, the fellows in Center of Synthesis and Chemical Biology, is actually, the head is Prof Sazali. Prof Sazali is not here. I tak bagi dia datang. Okay, and then the fellows, myself, Dr. Fazli and Dr. Nuhana. Okay, but we have associate members. Okay, our associate members, Dr. Tajuddin is a newly appointed associate members, and we have 3 labs under the Center of Synthesis and Chemical Biology. Institute of Science altogether ada 14 labs, 14 labs, 6 centers. So we have nearly 20 fellows. We have approximately 20 admin and support staff. It's a very huge center of excellence in UiTM. Betul tak, Prof Ada? Okay. So, but I just want to focus on synthesis and chemical biology. No hard feeling, Prof Rusuk. You are here, but I'm not going to talk about your center. Okay. Center of Synthesis and Chemical Biology, we have 3 labs: the Organic Synthesis Research Lab, Microbiology Research Lab, and Tissue Culture Research Lab. The Microbiology Research Lab and Tissue Culture Research Lab is headed by Dr. Nuhana, and these labs are in our main campus in Shah Alam. The Organic Synthesis Research Lab is not here in the main campus. We are in Puncak Alam campus, in bangunan FSG 234. Okay, kita menumpang FSG on the top floor, on the 9th floor. So it's a huge lab. I will show some pictures about our labs. We have NMR, mass spec, HPLC, FTIR. Elemental analyzer is currently under Dr. Karima, who is also a fellow of iOS, and then we have polarimeter. So basically, we have the required instruments to do research on organic synthesis. Okay, and like our Tuan Master of Ceremony just now mentioned, our group focused mainly on synthesizing 5-membered nitrogen hydrocycles with pyrrolidine ring system. We did a lot of chemical exploration on also fused bicyclic and tricyclic systems of these nitrogen hydrocycles, and most of the compounds that we synthesize for various applications, especially for therapeutic agents and also for organocatalysts or ionic liquids. I ada seorang PhD student kat belakang tu. Bila entah dia nak habis? Dia dah sembunyi dah, Aisyah. Okay, she's doing organocatalyst, okay, for her PhD work. So, for the past 15 years, we have many postgraduate students synthesizing bioactive natural compounds. Okay, so we did a lot of retrosynthetic analysis to synthesize all these compounds with specific potentials. Perusin, which is an antifungal alkaloid; streptopyrrolidine just now, which is an angiogenesis inhibitor; codonopsinin, which is an antihypertensive drug; dicidamide C, which is a protein phosphatase inhibitor. So, and we had some publication also regarding this. And we also do a lot of synthetic exploration on the pyrrolidine type of compounds, and we have also published quite a number on those research activities. And for the last 5 years, I think more than 5 years, we have started to synthesize compounds with a fused ring system. So either 2 ring systems or 3 ring systems fused together. So we synthesize lactone-lactam ring system, pyrroliquinoline, quinolactacin, lactam-lactam system. So our students are all sitting over there. Okay, so they synthesize all these kinds of molecules and did a lot of synthetic exploration. We also synthesize fused ring systems which are not pyrrolidine based. And we also help the industries, example the Samdabi, that means to convert their waste from their rubber production, that is L-cubicultol, to something that is of values. We convert the L-cubicultol, we help them to convert cubicultol to mannitol, inositol, and inositol triphosphate. We have some collaboration also with FRIM and also international collaboration with National Health Research Institute in Taiwan. Okay, so Sufri, less than 10 minutes. So these are the picture of our labs in Puncak Alam campus. We have a very huge lab. There are 12 film cupboards and 12 benches, if I'm not mistaken. I don't know. But I wonder, where are all these students? Ada seorang je duduk kat situ. Must be bulan puasa. They are all sitting. We have a resource room here and also a meeting room at the back behind the film cupboard. So these are just, this is our meeting room that is behind these two film cupboards where we have our annual, every fortnightly meeting, okay, progress meeting. And thanks to our researchers, and also we had postdocs, altogether 4 postdocs for the past 10 years, and our officers, Puan Zaleha and also Puan Afrida, and to all our postgraduate students of organic synthesis. Sorry lah, I did not list them you all up because ramai. So nanti kan Sufri marah pula. Explain to many of them. Thank you to all the postgraduate students for their work and their contributions to our research activities. And then finally, thank you. Now, before we ada Q&A, before I end, I have a bonus. This is a synthesis of Viagra. So anybody who wants to try, please screenshot, buy the required chemicals, balik buat. Actually, it was patented before, but bila patent dia habis, this was published in 1996 in Bioorganic and Medicinal Chemistry Letters, and the roots is very short root and non-organic chemistry punya root tau. Okay, boys and girls yang kat sana, propose to Prof Zali, you want to synthesize Viagra. Okay, there are only 6 steps involved. Okay, so with that, thank you once again.
Thank you, Dr. Zurina, for interesting talk. Now I would like to open the floor to questions and comments. Any volunteer? Any questions? Yeah, organic chem is quite difficult. I don't think so you can understand. So supposedly you have the questions. Can you ask? No.
Ada, Najmah nak tanya.
Okay, from friend to friend.
Dia daripada tadi nak tanya before I presented.
Tak ada. Okay, Assalamualaikum. My question is about organic synthesis. We know organic synthesis is making molecules, right? From scratch, we make molecules, right? And then we normally make molecules that have pharmaceutical values. That's what we normally do. That will be our target, right? Making molecules that have pharmaceutical values, right? So for a molecule, from molecule to go to the shelf of pharmacy, it takes years. And it takes a lot of, so many years and a lot of money. Okay, so my question is, what are the applications that this organic synthesis has that can we use in order to win research grants?
Or to win research grants?
Yeah, what are the applications that we can actually highlight other than these pharmaceutical values in organic synthesis? Because I'm organic synthesis and it's really being very hard for me to win a research grant. So what are the applications that we can highlight?
Okay, so it's true that most of the applications that we have is more on the pharmaceutical and drug related research. But you can also work together with people like from the polymer, for the, let's say, polymer people ke, ataupun advanced materials people, because researchers or scientists who's doing advanced materials, let's say for an example, to synthesize, I do not know, maybe like battery components. Because sometimes you can contribute from your knowledge what are the functionality in that organic molecules, the functional group or the substituents that contribute to enhance dia punya activities. Because maybe they just, for an example, I give you an example of kalau orang polymer lah, okay, because I mentioned that before. Bila dia nak they want to use a polymer in, let's say for apa, you give an example for untuk battery ke, as I do not know. Okay, maybe they have the substituents, but maybe you can discuss or describe the functional group apa yang contribute to increase the efficiency of dia punya interaction in secondary bonds ke primary bonds for your application. You have to discuss with them what they really want. Okay, so tapi like I've said before, because small molecules mainly on drug components, pharmaceutical industries, kita tak banyak sangat on, yes, that is inevitable. Even kalau kita nak produce medicine, we cannot work alone. We have to work together with biologists and pharmacists, okay, because they have to do the biological activity, they have to do the testing, clinical trial 1, clinical trial 2, betul tak? And then that takes years, 10 tahun, even 20 tahun pun ada, right? Because if we want to use our product, if you ask us what is the value of our products, the value is zero. The compounds that we synthesize, okay, let's say I synthesize, okay, let's say kita synthesize this intermediate, okay, what is the value of this intermediate? Tak ada value. And what is the value of this intermediate? Memang tak ada value. If we want to send out these compounds to abroad for animal studies ataupun for mass spec studies, kita declare in our form, kita kata bila when for apa panggil, selalu kita nak send compounds tu panggil apa? When we have to declare what is the value of our compounds, normally we say no value. Memang dia tak ada value. But kita contribute to new knowledge. So we have to work together with someone who can bring something out from what we have. So we have to work with the biologists, with the pharmacies, so that they can bring our compounds to that level that it has a values. Itu yang macam we work with National Health Research Institute, okay, because they promise they can say that they can do the testing for us. They somehow we can collaborate later, finding someone to do for our clinical trial 1, clinical trial 2. Kalau medicine atau pharmaceutical products, you really have to deal with you have to deal with human, betul tak? Okay, so that means you really have to do proper testing to make sure that is safe. Kalau tidak nanti kita kena sue, betul tak? So we have to work with someone. We cannot work alone. So that is the main thing. We are just a fundamental scientists who contribute to new scientific knowledge. Kalau nak apply grant for kalau fundamental research grant scheme tu, yes, we can go into total synthesis ataupun the fundamentals. But if you want to go into yang LRGS ke, TRGS ke, ataupun any grants which requires an application part, then you have to work with someone else. You cannot work alone. But you have to contribute your fundamental aspect. Okay?
Any other questions?
Okay. Assalamualaikum, Dr. Zurina. We normally hear, my question is very simple. We normally hear that, the synthetic chemicals, okay, maybe can cause side effects. And I think we normally, we hear about that thing quite a lot. So any comments about that? If you compare, let's say you mentioned about the Tongkat Ali extracts or compound, that you guys produce it synthetically. Okay, if you compare the natural compound, so which one is better to take? Not only Dr. Ali, I mean for many other things too.
Okay. Now,
Okay, thank you.
if you synthesize exactly the same molecules with the natural, there should be no problem. Provided you have to synthesize the same molecule lah. Faham tak? Like I've said just now, the natural compound, it has a specific structure, specific structural conformation. Maksudnya dia punya orientation of the molecules specific macam ni. So when we synthesize, make sure we synthesize the same structural conformation. Macam thalidomide tadi. Okay? That's why you need to have that acquired knowledge in organic chemistry, the fundamental knowledge, in order to do that, to synthesize that. Okay. Itu satu. Satu lagi, if you, yang kata side effects tadi, normally, maybe the new derivatives or new analogues. But when you synthesize new derivatives or new analogues, that is where you have to get someone yang not know organic chemistry tadi to come into the picture and help you to do further testing to make sure that dia, the best is kita kena buat research je lah to make sure yang dia tak ada side effect lah, kan? That means kalau if you do, let's say you have a molecule, you do antibacterial study contoh, okay, and then you do antifungal study contoh, you find out that this compound can be used as an antifungal agent, can be used an antibacterial agent, okay, and then yang side effect tadi, maybe along the way when they do the testing, yang clinical 1, clinical 2, clinical 3 tu, then they discovered that dia ada side effect. Then you have to do further testing to overcome those side effects. Tapi you have to look also, not all organic or synthetic compounds ada side effect. Ada synthetic compounds yang tak ada side effect. Tapi selalu organic compounds yang tak ada side effects ni, people tak highlight pula. Betul tak? Orang highlight only yang ada the negative aspect. Can you, if you dengar my presentation just now, I'm highlighting the organic compounds yang ada positive values. So there are a lot. There are 16 million organic compounds. Yang ada side effects je, maybe sikit je, a small amount. Okay? But the small number tu, it can be further tested and further modified and to make it better. So that is the point of doing research. Kan?
Maybe one more question. Last. Student? If not, I think I can give 2 questions at least. It's a MC lah. This is the responsibility.
Responsibility of an MC.
It's
ask
the
question.
MC. I have to ask question because I learn from you. When we have the iOS punya talk kan, MC have to give the question. Okay.
I've created a monster.
You have to listen it carefully. The title is quite interesting. Small molecules, big potential. So, in order to be used in industry, in terms of pharmaceutical or cosmetics, the organic molecule have to be functionalized. It means that the size of the molecules getting better, getting bigger. How do organic chemists define the size of the molecule? How small it is? Like in material, we know nanometer is the size of the smallest material. How do organic chemists define in terms of size, how small the molecule? The second question, what is the smallest molecule in the world that have very potential, have a big potential? The smallest but have big potential. You get my questions?
Okay. Okay, soalan nombor 2 tu dulu. Soalan nombor 2, what is the smallest molecules that have the biggest potential? I do not know. Ada 16 million organic compounds kot. I do not know which is considered to be the smallest with the biggest potential. Lagipun that soalan is very subjective, Sufi.
Yeah, because it's not an organic question. It's just
it's very
I just wondering because the title is quite interactive.
Okay. So, thank you very much, Mr.
Small
Chairperson.
molecule, big potential.
Okay. So, it depends on the individual. maybe one person would think that this particular molecule A to a small but has a big potential. Maybe another person will consider it to be not a big potential, kan? So it's very subjective. It depends on the individual. So if you ask me, I do not know. It depends on the individual.
Never mind, we are still okay.
Okay, question number 1. Tadi apa?
How do the organic chemists define the size of the molecule? How, in terms of number of atom, or what is it?
Okay. To us, kalau small molecules, like I said just now, those that I've presented here for an example on the slide, these are considered to be small molecules. Small molecules ni normally a molecule that have molecular weight, like I said just now, around 300 grams per mole or less. Maybe kalau lebih sikit pun, they are considered small molecules. But if, Sufri, pay attention, I'm answering your
Yeah, I
question.
get that. Because I was wondering whose cars that by the tree. It's just along the route. It's okay, just carry on the answers, please.
Okay. Now, if you have big molecules, okay, the big molecules like protein structure, okay, like the DNA, like starch, like polymers, they are big molecules. Sometimes you have also small molecules, but the small molecules have like nitrogen, oxygen, the atoms that contribute to hydrogen bonding, strong intramolecular forces. When you have those kind of molecules with that atoms, they tend to form supramolecular complexes. Then bila dia jadi supramolecular complexes, then you consider it to be a big molecules. But faham tak?
Yeah.
Okay. I think that will answer.
Thank you
So,
for the
again, it's very
any
subjective.
additional answers.
No.
Okay, thank you very much for the Dr. Zurina for the very interesting talk. Just join me to give the call for Dr. Zurina. It's a gesture of our gratitude. We would like to invite Professor Dr. Rozana Muhammad Dahan to present to Dr. Zurina the token of appreciation.